Good morning. Can everybody hear me?
Yes, I can.
Okay, good. And we'll get started. I see David's on there, one of my cohorts. Hey, David, if anything comes up on chat, would you just give me a nudge or let me know? So with that, we'll get started. My name's Larry Lemens. I'm the one of the service advisors for Gustav Larson, and we're just going to go over some condenser troubleshooting this morning. You guys are lucky it's the first class I've done like this, so it's kind of working the bugs out in front of you. So if you have any questions or any comments, please unmute yourself and let me know. We'll stop there and discuss it. So I guess with that, we'll get started. If anybody needs NATE continuing education, this qualifies. Shoot me an email or just let me know that you guys need it, and I'll send you the forms that you need to fill that out. So everybody can see the PowerPoint too, I hope. Okay, good, good. Just want to make sure before we get rolling here. So, all right. There we go. Threw this on there. Guy sent this to me from out west, but if the Coors can turns blue, that means it's properly charged, right? So beer can cold and sweaty. Just kind of a
yes,
joke.
sir.
Yeah, we'll work around that maybe a little later in the presentation, but I just had to add that one too there. So this morning, what I want to talk about is compressor diagnostics. We usually do a class about how to check superheat and subcool, and we're going to do something a little different this spring. It's how to verify you got a fan that's working properly or your compressors working properly, how to troubleshoot. I've got I got a video that's really good. It talks about scroll compressors. And then there's a new generation two-step scroll. And I don't know if we've spent any time on that in the last couple of years. So we're going to talk about that a little bit too. So as I said, if you got questions, just stop me or ask questions, raise your hand, do it that. One of the things that I from our side of the business, I don't ever seem to get enough information. So when you guys are calling me, I got to have model, serial number, get the voltage, the amperage, some temperatures, pressures. Just makes the job a whole lot easier on our part. We've also got the ability to, on our cell phones to get pictures, to get information, videos. Again, the more information, the better. So when you're on a job site and you're having issues with something, grab a ton of information and give us a call. Just make it a lot easier for both of us. One of the things that is out there that I get a lot of calls on is on the condensers. We've got PSC motors for condenser fans, and we've got ECM motors. The ECM motors are pretty simply regulated. It's an ECM motor, but we're using a simple 24-volt signal. So if you look, on some of the older equipment, we actually had 2-speed motors. We had a high and a low speed. On the new stuff, we don't do that anymore. We just have 1 speed. So, the yellow-brown wire, it's a 24-volt signal to the motor for low speed on some models. And on the yellow-white wire, we get a 24-volt high speed. So on the ECM motors, what you'll probably see is a blue and a yellow, or blue and a red wire going to the motor, or blue and yellow. That's a 24-volt low voltage signal. And there's also 230 volts going to the motor. And the 230 volts is there at all times. And what turns that motor on is that 24-volt signal. Okay, so if you want to troubleshoot these, if you've got 24 volts to the motor and you've got 220 volts or 208 volts to the motor, and the motor's not running, it's probably a bad motor. It's pretty simple to troubleshoot. If you don't have the 24 volts to the motor, it's probably something in the low voltage circuit. If you look at the wiring schematics on these units with the ECM motors, that voltage comes right off the low voltage contactor. So when you energize the contactor to bring the compressor on, that should energize this motor, and that motor should run. So again, if you don't have 24 volts there, then it's something in the wiring or in the contactor. It's elsewhere down the line. But that's the real simple troubleshooting on these is voltage is there, it should run. If it's not there, it won't run. So again, if you have questions on any of this, give us a call. This is in the schematics with the units, okay? Now, the more common thing that we see out there are PSC motors. And they've been around forever, but on those, you want to look at the capacitor. I think just about everybody has capacitor testers on their meters nowadays. The key thing with the capacitor, of course, turn the power off, disconnect the wires, make sure it's discharged. But check your capacitor out, make sure it's within plus or minus 10% of the value stated or listed on the capacitor. When we're looking at the motor, check for ground, check for the wires to ground. Check the windings, make sure we have some resistance on the windings. If a fan's running backwards, and I get this call every now and again, it could be a couple things. It could be the start winding is burned out on the fan motor, and the run winding has the ability to turn in either direction at that point. Okay, so start windings are out. It could run backwards, it could run forward. It's kind of a hit and miss kind of thing. If the capacitor is bad, it could start in backwards, or the run and the start wires could be reversed. I've seen that every now and again. Somebody will put a motor in and get the run, the start mixed up, and it'll run backwards. So on the condenser fan motors, just make sure the wiring's correct, the capacitors are good. Check your windings out. So just a few things to check when you're looking at a condensing unit. Again, when you're checking capacitors, turn the power off, discharge the capacitor, check the capacitor out. Make sure it's plus or minus 10%, like it says on the capacitor. With the voltage on, measure the voltage at the load side of the compressor as the compressor tries to start. And the next slide will show this, but if it drops below a certain voltage, this compressor may not start. So, at rest, you may have 220 volts, but if you try to start that compressor and it drops below 187, that compressor may not start. You have a voltage issue at that point. Okay, so we have to look at wires. We have to look at different things in the system to see what's going on with the compressor or the wiring to the compressor. The other side that you have to be aware of is the high voltage. So make sure that we're not exceeding 253 volts while starting. The windings and the insulation on a lot of the components aren't going to take that high voltage, and it's going to shorten the life of the compressor, shorten the life of the contactors, the boards. Just make sure we have a voltage that is between that 187, and I think 187 is a little on the low side. A lot of manufacturers will say 197, which is I would tend to agree with. But definitely at 187, you're going to have issues with units not. If there's a voltage drop, look for proper wire size, look for melted wires. Just kind of do a visual inspection. If it gets into the power feeding the unit, that usually ends up on the electrician. Sometimes we'll have units changed out in the field and go to a bigger unit because it wasn't big enough for the house. And then the existing wire may not be big enough for that, so the electrician may have to pull a new wire at that point. Check for voltage drop across the contactor. Put your meter across there. It should be, you know, it should be 0 voltage drop across there. So if you're getting a voltage drop across the contactor, that means the contacts are burned or pitted. Things are just not, you know, the way they should be. Contactors are pretty cheap. So if you suspect the contactor, back in the old days, we always carried contact point files and we would clean the contacts, but you know, put a new contactor in if you suspect that there's something going on with it. It's just cheap insurance for the life of the compressor. Okay, so if we've checked out the voltage side and we see everything's okay and we still have a compressor that's giving us problems, next thing you want to do is ohm out the compressor. Now, I realized getting to the compressor isn't always the easiest on some of these units. So if you can disconnect the wire back at the contactor, and I've got some slides later on to show how to grab those readings, but you can do an ohm reading or a ground reading through the harness that goes to the contactor. Just make sure that you disconnect the wires, okay? Single phase units, what we want to do is we want to check, you know, common to run, common to start, and then of course start to run to see that all the windings are in good condition. And then we also want to go, you know, to ground to make sure we don't have a ground on any of the windings. So if you do a ohm value or ohm reading on a single phase compressor, common to run is going to be the lowest value. Okay, run is always the lowest value, and it's typically maybe around 1 ohm, 1.5 ohms, somewhere in that area. Okay, common to start is the second lowest. The start winding has more resistance because it's you know, it's there to start the compressor, and then the total of the two should be our start to run. So if you ohm out the common to run low value, the common to start second lowest value, add those two numbers together, common to run should be should equal that number. Okay, and of course, you know, ground should be 0. Again, just a close up on there, you know, common to run, common to start. And they're not always marked on the compressor. So if you know the numbers, you can actually, you know, write down on a piece of paper your common, or put your 3 terminals down, take some ohm readings. So if I go common to start and I see this value, say is 2, common to run is 1, and then I go across these 2 and I get 3, you know, that's the total. That tells me right there, that's my run and start. And the lowest one is run to common. So you can pin which one is your common run and start if it's not marked or if it's you can't see it. There is a way to figure out which is which on there. And again, on some of these units, if you reverse the start and the run, you could have the compressor running backwards. Does someone have a question? Or? Okay.
Larry, there is a chat question there.
Yeah, okay, what do you have? I can't see it here, but let me take a look. Where's my chat? Oh, here we go, okay. Sorry about that, my chat doesn't pop up on the screen for some reason. Here we go. Is it okay to pull leads off the compressor to check windings with unit has a charge? Heard not to do that. Oh, you mean for fear of losing the charge? As long as the power's off, and it shouldn't be an issue. I mean, I think it's done all the time. The one thing you don't want to do, and I cover this a little bit later, is you never ever want to put power to a compressor in a vacuum. Okay, because when you put a vacuum in a compressor, it changes the insulation value based on the atmospheric pressure. And you could have a lightning storm in there and you could burn out a compressor and blow the plug out. But with the charge in the compressor, I don't think it's going to be an issue. Okay, there we go. Okay. All right. So that's a single phase compressor. Anybody have questions on anything we covered on the single phase? All right. So what I want to do is I want to talk about 3-phase compressors, and they look similar. The The pins are, they look almost the same. The difference is they're equal resistance. So when you're ohming out a three-phase compressor, you've got L1 to L2, L2 to L3, and then L3 to L1. And you take that ohm value, and that should be plus or minus 2%. I mean, if it's 1 ohm, 1 ohm, and 1 ohm, it should be like 0.9 to 1 ohm, maybe 1.1 at the most. If you get into inverter drive equipment, and I didn't put anything on inverter driven equipment in here, and that includes the Mitsubishi, the variable speed condensing units, heat pumps. Those typically are a little lower. They're like 0.7, 0.8, sometimes 1. Some of those are down to 0.2 for ohm value on inverter driven equipment. But that is basically a three-phase compressor also. So you ohm them out the same way. The difference is, if you look at a true three-phase compressor, it's going to say L1, L2, and L3. And on an inverter-driven piece of equipment, you're going to see U, W, and V. That's an international symbol for inverter-driven equipment. So if you see U, W, and V, that's a three-phase inverter drive compressor or inverter-driven motor. And they're a little bit different. Usually the higher the voltage, the lower the ohm value. So on a 440 volt three-phase compressor, you're going to see ohm values in the 0.6, 0.7 range. On a 230 volt system, you may see a little higher, 1.1, 1.5, something like that. But if you're not sure, give us a call or look it up in the service facts. The ohm value is available for those units to make sure you have proper ohm value. But again, three-phase is a little bit different. Again, three-phase units, we don't use capacitors, we don't use hard start kits. Three-phase units are very efficient and they work pretty much the same, but the ohm values are quite a bit different. Again, a close-up of a three-phase, and they may not be marked also, but remember, equal resistance, no capacitors. All right, on single-phase units, you may find start components, you may find SPP, 6 and 5 hard start kits, you find start capacitors, relays. If you don't have it on there and you're having problems with a compressor that doesn't want to start, say it's got locked rotor or it just doesn't want to bump, doesn't want to move, you can add a hard start kit. I'd prefer that we put a factory hard start kit in here. And you can also try to bump them backwards. Sometimes you can take the run and the start wires, reverse them, and just give that compressor a quick bump. And that's basically, if anybody's ever seen an ANI, an analyzer, compressor analyzer, that's basically what you would do. You just give it a quick bump backwards to see if you could break it free. If you do that and you try a hard start kit and you still can't break the compressor free, it's stuck. It's going to have to be replaced at that point. But there are some components available on the single phase units that we can add to try to do that. Now on a three-phase unit, if you got a stuck compressor, you can try reversing L1 and L2, momentarily bump it and see if you can break the compressor free. They'll spin it backwards. Sometimes if you do that, you can break them free, reverse the wires, and the thing will run again. Although it may fail down the road. If it's been stuck, it's stuck for a reason. So, but there is a way to do that to try to get things running, to see if the system will work. Potential relays, and you see these on our hard start kits. If you buy a Train or American Standard hard start kit, it's got a potential relay and a capacitor in it. Copeland uses these. They're pretty universal. There's different pickup and dropout voltages, so you can't just throw a generic on there and expect it to work. It could be that it's a higher voltage, lower voltage, and if the voltage doesn't come up to speed, like if you're running low voltage, these things will stay in the circuit and then eventually burn themselves out. So pickup and dropout voltage is important. Make sure you match that when you're replacing a start relay. If you want to test them, the terminals are labeled 1, 2, and 5. terminal 1 and 2 are normally closed contacts, and that's what goes to the start winding. And then as the compressor starts and the voltage comes up, it opens that contact and it pulls that start capacitor out of the circuit, okay? Measure the resistance between 1 and 2. It should be 0 ohms. So terminal 1 and 2 are your normally closed contacts, and that should read 0 ohms. It should be like a closed contact. Okay, these are, and by the way, these are position sensitive relays. You can't put them sideways or upside down. They depend on gravity to hold that contactor closed. And as they energize, the coil picks up and opens that contact. So if you grab the unit and put your leads on terminal 1 and 2 and just shake that unit a little bit, the contact should open. Okay, and if it shakes and you can hear something moving in there, that means that the solenoid is free and the contactor is probably okay, or the start relay is probably okay at that point. The next thing you want to do is ohm out terminals 2 and 5. That's your relay. That's your coil relay. That's what you energize to open those contacts. If that's open, you definitely want to replace that relay because it's burned out at that point, and it won't take itself out of the circuit. And that's typically what will happen is if the start relay fails, the coil will fail, and it won't take itself out of the circuit, and you'll see capacitor failures. So if you see a capacitor failed on a start relay and you're not sure what the cause was, just replace both of them. Don't replace just the capacitor, replace the relay and the capacitor. Let's see here. All right, just checking chat to make sure we're okay. Everybody, anybody got any questions? All right, so there's basically, I should say, there's two different kind of compressors that we really deal with. We're not talking about the big stuff, the screw compressors, that kind of stuff. We're talking about scroll, which is probably 95% of what we see out there. And then I've got a little bit on recip compressors, which are going by the wayside. You know, there's more and more retrofit kits that are changing those over to scroll anyway. But scroll compressors have been around for a long time. There's some new technology. If you haven't really sat down to see how they work, I've got a video I'm going to play that does a really good job of explaining how scrolls work. But basically, it's a moving scroll plate and a fixed scroll plate, and the motor turns and it compresses refrigerant in that scroll section right there. Some of the compressor is oil, and then of course we've got our return, our suction, and our discharge on the unit right here. You know, it's created by moving these scroll plates, and the video is going to do a much better job to show exactly how they work. And even though I've been dealing with scroll for probably 30 years or better, it's still kind of neat to see how it works. So with that, I'm going to just drop out and play this video. And I hope this works, because every time I try to do this, I have issues with it. So bear with me here. Can you guys see this screen here? And let's see, I gotta do this. Where are we? Okay, share. Video. Optimize. All right, can you all see that? Can you hear that, Joe?
A scroll compressor is also known as a scroll pump and consists of a shell with an in and an outlet. The lower part of the shell contains the lubricant, which is used, for example, to lubricate the plane bearings. A motor sets an Archimedean scroll, which is found in the upper part of the shell, in motion. The scroll housing has an inlet, as well as a discharge port, and a fixed scroll. Here, the scroll housing is made transparent. The scroll housing has a base plate. The fixed scroll is attached to the underside of this base plate. For better visibility, only the moving scroll with its base plate and the fixed scroll are now being displayed. The gas is absorbed in the forming chambers, and transported to the center of the scroll set. As the rotation progresses, the chambers become much smaller, so that the gas is compressed within the compressor. Therefore, this type of compression is called internal compression. In the middle of the scroll housing, which is shown here in green, is a discharge port, through which the compressed gas can escape. Normally, there is also a check valve. Today, there are several compressor designs. On the one hand, the movable scroll can move with an extremely small distance to the other scroll. The scrolls therefore do not touch each other. On the other hand, there are also designs, in which the scrolls are in contact. Such scroll compressors usually have a better seal, and thus, a higher efficiency. Axial sealing can also be designed in various ways. One possibility is the use of a floating tip seal. These are present on both scrolls and are pressed against the base plates by gas pressure. In this animation, the upper base plate is not shown. Scroll compressors are used in air conditioning systems and heat pumps. When used in cars, they are known as scroll-type superchargers. The small number of moving components results in a high level of operational reliability. Due to their special design, scroll compressors are also highly efficient. In addition, noise emission of scroll compressors is quite low.
All right. All right. There. Okay. Get back to where I was here. Any guys got any questions on that? It's actually kind of neat technology, and I thought it was a pretty good video to share. Let's get back to share my. Okay. So that's the basic, I mean, that, excuse me, that's how all scroll compressors work. Now, if it's a single stage scroll compressor, it's just going to pump, continuously. And like you said, there's a check valve in there. In the old recip compressors, which we'll get to, we used to use a set of valves, or actually reeds, little reed port valves. And that was also your check valve. In the scroll compressors, we don't have that. So somewhere in the system, there's usually a check valve. So if you ever hear scroll running backwards on shutdown, that means that check valve probably quit working or is not working. So, be aware there is a check valve in that scroll or in that compressor or in the line to the compressor to make sure we don't run backwards. So when you get into the two-step, we call them two-step scrolls. The scroll runs at the same speed, okay? It doesn't change speed. What it does, it has kind of an unloader, and we're going to talk about those a little bit. I'll share with you how those work. So if you want to see if a two-step scroll is working properly, the first thing you do, of course, is put an amp meter on there to make sure that we're drawing proper amperage. And When it goes to second stage, it's going to increase the amp drop maybe 20, 25%. You know, when you're looking at a compressor that's only drawn, you know, maybe 15, 18 amps, 25% isn't a lot. It's a couple of amps, you know, in a lot of cases. So it's pretty hard to see. But there are some other checks that you can do when you're working on two-step scrolls. Okay, so on two-step scrolls, what you're going to find is you're going to find a rectifier, usually on the wall inside the control panel. And it's going to have a yellow and a blue wire, and then it's going to have two white wires, okay? If you look at the rectifier, there's two dots, there's two white dots on there. That's where the two white wires go, and those are DC. So what we're doing is we're taking 24 volts AC, running it through the rectifier, and dropping it down to 15 to 18 volts DC on those white wires going to the solenoid in the compressor. And that's what your Y2 does. So when you're working on a two-stage or two-step compressor, Y1 energizes the contactor to bring the compressor on, and then Y2 energizes this rectifier to energize the solenoid in the head of the compressor. So if you have a problem with the solenoid, say the solenoid shorted out or the rectifier shorted out, what can happen is when you energize Y2, it may blow the fuse on the board, on the furnace. And I run into that every now and then where if the fuse is blowing on the furnace intermittently or you're having problems with that, you know, start checking out, ohm out your Y2 circuit, see if you have a ground or a short somewhere. Because if you do short out the wires to the rectifier, it could be a bad rectifier. It could be a short in the solenoid in the head of the compressor also. And by the way, if the rectifier is bad, not a big deal. You just get a new rectifier, put it in there, and you're good to go. If the solenoid shorts out, you have two choices. You can either change the compressor or just let it run in a low stage. But there's no fixing it at that point. Once it burns out, it's a new compressor or run in a low stage. And that's basically what it shows here. Look for AC volts feeding the rectifier, and you know, check for DC volts coming out of the rectifier. And here it says 15 and 27 volts should be present somewhere in that area. A little different picture. This just kind of shows the wiring schematic. It's basically just a, you know, it's a rectifier and it loads the solenoid in the compressor. Okay, so if you want to ohm this out with an ohm meter, if you got, you know, infinity or zero resistance, you got a bad rectifier. Some other things on the two-step scrolls, you've got some other components. There's a temperature control for the crankcase heater. There's a high temperature switch to shut it off if the discharge gets too warm. And the little container there that says, "What is this?" That's not a dryer, that's a muffler, okay? The reason I talk about that is because I have had guys in the field think that was a dryer, and when they put the compressor in, they put a dryer in there. Dryers do not do well in the discharge of the compressor. They belong in the liquid line after the condenser. Just make sure you never put a dryer on the discharge of a compressor because it melts the desiccant and sends it out into the system, plugs up everything. So that is a muffler. That does not need to be replaced. That can stay in the system unless you have a really, really bad burnout. That really doesn't need to be replaced. So you just, you know, be aware of that. The low voltage terminal strip on the compressor looks like this. Okay, it's got the two white wires going into it, and that's the 15 to 27 volts DC. And then the line voltage, of course, is on the other side. Again, if you want to ohm out the compressor, it ohms out the same as a single phase compressor, just like we talked about earlier. And the low voltage, again, ohms out as the low voltage side, 15 and 24 volts, or I mean for voltage, and then ohms out. I'd have to look at the ohm value for that solenoid. I'm not exactly sure what it is, but if it's open or if it's shorted, it's bad. All right, we've got a low pressure switch. All of our units have low pressure switches on them. They don't have high pressure switches. Reason being is if you get to a high pressure situation, it's going to trip the internal relief valve, and that's going to throw hot gas on the temperature cutout, the internal temperature cutout, and it's going to shut the system down. So but we do add low voltage switch or low pressure switches to our units. All right, two-step scroll. It's a little different. It's got a unit on top of the compressor. It's got a little solenoid actuator in here. It's got a modulation bypass ring. And basically what it does is when this solenoid is not energized, it bypasses refrigerant back into the shell of the compressor, about 20%. And when it energizes, it slides this scroll plate ring just slightly, misaligns these holes, these bypass holes, and it pumps 100% into the system. And here's a picture of it, what it actually looks like. So here's your two wires feeding that solenoid, and here's the little spring-loaded solenoid in the unit. It just moves this scroll plate right here and just misaligns this bypass ring here, okay? And that's all, basically all it does, is it just either pumps 100% or it pumps at 80%. All right, now this is a animation of a two-step scroll, the new design. Now we've got, these aren't, I don't think they're out yet, but they're coming. So it basically is the same compressor. It's got the scroll set in there. It's got the bypass ring on the top for two-step scroll. The difference is this one works off of a three-way valve instead of a solenoid, okay? So it basically does the same thing, takes in gas, runs it through the scrolls, pressurizes it, and sends it into the system, okay? When it's in part load operation, what it does is it bypasses back into the shell. And when it's in full load operation, it pumps 100% out. So this is basically showing you bypass and full load. So what it is, it's just a three-way valve here that moves back and forth, and it just diverts the gas. And that's how the new two-step scroll is going to operate, and as they come out. Shouldn't change the noise, the sound, the amp draw. It shouldn't change any of that. It will change the efficiency, or I guess longevity. The solenoid is it's kind of the weak spot. This three-way valve is probably going to be a lot more reliable. So, and basically that's all. It does the same thing. Here's the old system with the solenoid valve, and it just moved the scroll plate a little bit. The new system, all it does is it changes the direction of gas in through this portion of the scroll here. So that's what we're going to see. As far as I know, I didn't get an answer on it, but I think these are powered by DC voltage, just like the solenoid is. So shouldn't change anything on the other unit, just the way that it actually modulates inside the head of the compressor. Questions on that, anybody? Okay. All right, so that's scroll technology, and that's where we're going. I would say recips are probably not gonna be around except for the really, really small stuff, reach-ins, that kind of stuff, and that's even turning into more scrolls and inverter-driven equipment. But when you looked at the old recip compressors, basically what it was an electric motor, a crankshaft, and a piston. Okay, and a set of reeds here, and the piston would pump up and down, and it would just draw the refrigerant in across the coil, across the motor, run it through the piston chamber, pump it into a high pressure gas, in and out to the system. The nice thing about the recip compressors is they were not polarity sensitive. Three-phase compressors could run backward or forward. It didn't really matter because it was just a crankshaft turning with a piston. So as far as the piston knew, it didn't really care which direction the shaft was turning. So that was kind of nice. The new ones, the scrolls, are are sensitive to that. You can't run a scroll backwards for very long anyway. They'll run for maybe 15, 20 minutes before they'll do something major and take themselves out. So that's why on the new ones we put phase protection on all of our commercial equipment. Now on the old system, we had a set of reeds. Here was the valve. So every time the piston would come up, it would discharge through the valve. And then when the piston would go back down, valve would close and it would draw the refrigerant back in through the ports. You know, pretty simple operation. You know, they don't like liquid. If you start putting liquid into a piston, it takes those valves out pretty quick. Now,
That's the Larson Company, Jeff speaking.
yeah, on
Yeah, I've got it here. Do you have a PO for me, or?
I'm gonna mute everybody. There, we're good. Okay. So on the old ones, if you wanted to do a pump down test, you could do that. On a recip compressor, you could put a valve, you could close the discharge valve, put your gauges on there, pump these down to 0. You could probably pump them into a vacuum. Turn the power off, and the refrigerant charge would just stay in the outdoor unit. If it didn't, if it leaked back out, it probably was a bad valve. That's how you tested the valves on the old ones. So you'd put your gauges on, close the discharge valve, and pump the unit down. And you know, if it was good, it wouldn't leak through the valve plate, and it would hold vacuum. And that's how you did a valve plate test. That also tested your high side and your low side. So if the compressor had the ability to pump it down, that meant it could pump against a load. And it also meant that the valves were working properly. Now, you can't do that with a scroll compressor. They're not designed to pump down. So if you try to pump down a scroll compressor, what's going to happen is you're going to get down to about 11-to-1 ratio, I think is what it said. And you're going to blow the internal relief on the compressor. So you'll hear a whoosh of gas, and it will trip that internal relief, shut itself down. And that's by design. We don't want to pull a scroll into a vacuum, because if you do that, you're going to suck the oil out of the base and you're going to start to run the bearings dry. So scrolls, you can pump down to a degree, but you can't get them down to that 0 like you did before. So when you get to a certain point, you're just going to have to recover the rest of the refrigerant on a scroll system, just the way they work. And that, again, that's by design. So so if you run into some old pump down systems in the field that have recips on them, the scroll may not be a good match for that unless you make some adjustments to the system. All right, so there's a couple different ways that we meter, and I'm throwing these in here for a reason, because if you're using a flow piston and you shut the system down, the pressures are going to equalize pretty quickly. Okay, so if it's an FCCV, a flow piston cap tube, you run it in the system, you shut it off, the high side and the low side are going to equalize pretty quickly. Okay. If you're using an expansion valve, the valves that we put on our equipment, the pressures do not equalize very quickly. So in other words, if you're running a system and you got, say, 110 on the suction and 350 on the high side, and you shut the system off, what's going to happen is it's probably going to stay there. Okay, so the 110 and the 350 are not going to change. These are hard shut off expansion valves that we're using. They're externally equalized, but that doesn't mean that it equalizes the pressure. That means that it's referencing the exit pressure of the evaporator to properly flow the refrigerant into the system. So just remember, when we're doing compressor tests and we're looking at compressors, if the pressures don't equalize in the system with an expansion valve, that's perfectly normal. Okay. Same thing with an electronic expansion valve, and you're seeing more of these in the field. And if you look at an electronic expansion valve, what we have is we've got a stepper motor. Okay, we've got the valve, which is a needle valve, which is spins by the stepper motor. And then instead of using a capillary tube, what we're using is a thermistor and electronic board to control that operation. It does the same thing. It meters the refrigerant the same way. And again, it helps protect the compressor from flood backs, but it's an electronic version of a TXV. So Again, stepper motors are usually 12 volts DC. And these also, when you shut the compressor off, a lot of times they'll go to a minimum position and the pressures won't equalize, at least not very quickly. So again, when you're doing compressor diagnostics, don't look for those pressures to equalize quickly. They may not, okay, unless you've got a flow piston in there. On three-phase scroll compressors, again, make sure the unit's running in the proper direction. If the compressor is running backwards, it will be excessively noisy, and I'm sure you guys have all heard that. That's why we put phase monitors on all of our commercial equipment now to make sure we don't run a compressor backwards. They don't last very long when you run a scroll compressor backwards. They've got to be in the right rotation. But just make sure if it is in the wrong rotation, reverse any two wires, L1 to L2 or L2 and L3. Any two wires will change rotation of a three-phase contactor. And again, look at the contactors. Make sure the contactors are good. Make sure they're clean. Testing for damaged bearings. Well, there's a couple of things that can happen. If you've got a compressor that's running hot, again, verify we got the proper charge. And if we have the proper charge, then let's take some amp readings and see where we're at. If it's a three-phase compressor, you should get equal resistance or equal amperage on all three legs. If you're looking at a single-phase compressor, what we want to do is make sure we take a amp reading on the common wire. I mean, we can do the run and the start separately if you want to, but the common wire is going to be our true amperage. And if we've got an amp draw that's 15% greater than the data, we may have a problem with bearings in that compressor. It's going to run hot. At that point, you may want to, suggest we put a new compressor in there. If a compressor is running hot and we're having drag on the bearings, eventually we're going to have mechanical failure. We could have a burnout. And you guys all know, anybody that's tried to clean up a system, once it's gone that far, it's a bear to clean up. It's a lot of work. So it's always a good thing to grab an amp reading on there compared to the plate. And if it's out of spec, I mean, take a hard look at it. It may be a compressor that's just going bad. On three-phase equipment, we probably want to make sure we've got a good balance on the voltage, okay? It's important to make sure everything, the power is right, the voltage is right. And the way to do that is take some voltage readings, line 1 to line 2, line 2 to line 3, line 2 to line 3. Just make sure we get all three voltages and see where we're at. They should be typically pretty close, usually within a couple of volts of each other. If you see something that's out of whack, like in this example here, you probably can tell right now there's going to be an issue. But what you do is you add up the voltage of all three, divide the readings by 3, which gives you an average voltage of, in this case, 226 volts. So what you do is you take the voltage that's the farthest away from the average, in this case it would be 221 volts, and do the math. Divide 221 by 226. And what you get in this case is 97.8% or 2.2%. You're allowed a 2% imbalance on three-phase equipment. So at 2.2, that's out of spec, okay? And that could be an issue. Well, actually, it is an issue. You have to be careful with that. 2.2 doesn't seem like much, but it's enough to cause problems with the system. So if you have a voltage imbalance, if you're having issues with it, the first thing, of course, is make sure you've got, the proper wire size. Second thing, make sure you check the line voltage connections, load center distribution. Make sure we don't have any loose connections, bad breaker, any of that kind of thing. And if that looks good, the best thing you could do then is call an electrician or get your local utility involved, because somebody's got to balance the load, and balancing a load is not that simple to do. You've got to start moving breakers and doing different things in the panel. So You know, identify the problem, and then if you don't see the simple fixes, you know, get electrician on board or the utilities if necessary. But it's so important for this reason. If you have an imbalance of 2%, it means that your windings are going to run at 8% temperature increase in the windings for every 2%. So if I've got a system that's 10% off, you know, as far as balance, if you do the math, I'm going to have a 200% temperature increase in my winding. So the big deal here is, as the voltage imbalance increases and the amp imbalance increases on these, the windings start to run hot. So that could be a big issue. And if you're talking about a 3D compressor or a 4D compressor, you know, that's a lot of heat, and that's not a cheap compressor to replace. So again, it is a big deal. So if you're on 3-phase systems, just make sure that you take a good look at the voltage imbalance. Okay. What I've got here, this is how to test. We kind of went over this. It's how to check the voltage and check the ohms on a compressor to make sure the compressor is working properly. So what this is showing is, that's your overload. The circle here is your overload in the compressor, and this is internal to the compressor. So if you want to do some ohm readings with the wires connected, just make sure that somewhere you disconnect the wires from the system. So if you pull the plug out or disconnect them at the contactor, that's fine. But make sure that this is an isolated circuit if you're looking at the wiring schematic before you start doing ohm readings, because you're going to get backfeed. If you leave the wires connected and you start doing ohm readings, you're going to get backfeed through these circuits and these contactors and different things. So anyway, pull the wire plug, and then we can take some ohm value readings. So if anybody wants to write these down and do the math, you're welcome to. But if I take an ohm value reading between common and run and I see 1.2 ohms, that probably looks okay. I mean, that's a good ohm value for a run winding. So if I take a ohm value between common and start, I might see 2.3 ohms. Again, that's probably a fairly comparable reading that you'll see in the field, you know, 2.3. And if I go between run and start, and if you look, all we're doing between run and start is we're adding the value of these two windings together, and that should equal the total of the first two, which in this case it does. Okay, so if I was to read, you know, 1.2 here and 2.3 here, and all of a sudden I read, you know, like 2.2 here, that would tell me that somewhere I have a shorted winding inside that compressor. So it should all add up. It should add up to the value of these two different windings. And that's all we're doing, is we're taking a reading through the compressor through both sets of windings instead of going back to ground. If I go from start to common and I see OL, that means either my thermal limit is open or my start winding is open, one of the two. But we're definitely not getting a reading through here, so it could be either one of those. Same thing here. If I go from run to common, it could be my thermal is open, or it could be one of my windings is open. It could be my run winding open at that point. We really don't know which it is. But if I go from start to run and I read 3.5, then I know it's my thermal limit that's open. Okay. Now, if the thermal limit's open and the compressor's hot to the touch, give it some time, cool it down, see if it closes. It might have been just running warm. If the compressor's cold and this thermal limit is open, then you got a bad thermal limit. The compressor needs to be replaced at that point. So, of course, it could be, again, like I said earlier, it could be open start winding, could be open run winding. And go to ground. Make sure that between start and run and common to ground, we have nothing. It should be 0. Okay, well, not quite 0. So what happens when I have electrical issues? And these are just some pictures that Ethan shared with me, so I'm going to share them with you. If I have blocked rotor situations, these things are going to run hot. If I've got a compressor that's seized up, eventually it's either going to trip the thermal or the internal limit, or it's going to burn something up. It's going to have a what they call a thermal event. So if you do use mega ohms, okay, mega ohms are a good way to look at things if you have a record. If you just put it on there and try to determine if it's good to ground or if there's something going on with the system, it may not always be the best way. But this is just kind of a chart that says if it's 1,000 to infinity, it's in good condition. If it's 500 to 1,000, it's in good or excellent, then good condition. If you have, it'll show up. If you have a ground, it'll show up. So these are the values that you're looking for if you're checking for ground compressor. This is a start winding failure on a compressor. I don't know if anybody's ever seen the internal of one of these, but that's basically what the motor looks like with a start winding that burned out. And again, start winding burnout could be a stuck potential relay, could be could be almost anything. So again, another picture of a winding burned out. What the inside of the motor looks like, the rotor or the stator part of it. There's another burnout. So you can imagine if you have problems with electrical problems with a compressor, all this crap is going to be in the system. It's going to be in the oil. It's going to be in the refrigerant. It's going to be out in the system. So, if you can catch a compressor problem early before it gets to this point, you can save yourself an awful lot of cleanup time. Again, another close-up of that. That's what the oil looks like. It looks like black gold when it's burned out. So, all right. We're going to take about 10-minute break, guys. And I'm just going to touch real quickly on proper airflow and proper charging. With that, we'll come back at 9:05 and we'll spend about just a short time on that. So questions at this point, anybody? Okay. I'll see you about 9:05 then. I can't hear anybody. Yeah, I'm kind of ahead of really. I didn't know. I gotta feel like I'm more just gonna do some quicker stuff on monitor here. Thanks. Oh no, that is are you still looking at it? It's my clock. It's my clock. No. I didn't, no, I did not, because I'm not seeing chat. Yeah, I'm in full screen, so I'm not seeing them, I'm not seeing anything. I gotta change that. Yeah. I gotta, if I put chat on, then I can't see the screen. I don't know. There's things that are working. Yeah, I might have to do that. See, I did share full screen, so I can use that. But anyway, thanks for the feedback. I do so. I changed a lot of stuff. I'll send you the thing over. So I gotta run and get the next segment. Here we go. All right, is everybody ready to go here? Let me all right. I think on the web meeting we went till 9:30, so I'm going to just kind of push through some charging and airflow stuff pretty quickly here. It's the first time out, so we weren't sure how long the compressor section was going to go, but we got about a half hour. So if you got any questions, unmute yourself and just jump in. Give me some direction here, and I'll go where you guys want to go. One thing I want to put out, this is a training sheet that I use. We talked about getting information. If anybody wants to shoot me an email, I'll send these forms to you. But basically, when you're looking at the refrigeration side, we've got the compressor running, everything's working. Then we want to look at the numbers, the temperatures, the pressures, check out the subcool, check out the superheat, wet bulb readings. We got to know what this information is in order to do a good job of troubleshooting these systems. The other thing I want to point out to anybody out there that's interested in continuing education, you go to fieldtechhelp.com. There's a learning center in there. There's a bunch of free videos. You can sign yourself up to do learning classes. It's free, doesn't cost you anything, and it's great information. So I use it all the time. Good site. Airflow, again, we call this the low bid. That's a twin system. That's a twin rooftop. So, and then again, here's another one we call the low bid. But all kidding aside, airflow is important. Everything that we do in this industry is all wrapped around airflow. Is the filter clean? Is the condenser coil clean? Before we start adding refrigerant or before we start doing anything major to the system, make sure we've got good airflow. It's just key to everything we do. And I know you guys are going to get calls if it ever gets warm here. And people are going to say, my AC's not working, it's not doing this, not blowing any air. And you'll get there and there's a brand new filter in there, because between the time they called you and the time you got there, they realized they forgot to change the filter. So, but again, airflow is everything. One of the things that I want to point out on the Trane American Standard equipment is when we went to these new motors, the redesigned furnaces, we took into account that 0.7 is really the new norm. And if you're doing static pressure tests, it's impossible to get to 0.5 static anymore. I mean, by the time you put a coil in there and a high efficiency filter, you're going to burn up that 0.5 pretty quick. So in all reality, if you're at a 0.7 or a 0.8 static, you're probably in the realm of where you should be on a system. Static pressure measurement, again, it needs to be between the filter and the blower for the return. It needs to be between the A coil and the heat exchanger for the supply. Add them together, and that's your total external static. And I know I'm going through this kind of quick, but we're a little pressed for time. But setting the airflow on the S9Vs, one of the things that you'll find on the S9V furnaces is that you can fine tune it pretty easily. I mean, you can set the tonnage, you can set the CFM per ton, and the furnace will dial itself in. And if you look at the blower curve, it'll move the right amount of air, based on what you're set for. On the S9Xs and the S8Xs, it's a little different. We have some 5-speed motors out there, and we have some 9-speed motors out there, okay? And if you look, yeah, here's the one I wanted to get to. On the 9-speed motors, depending on the static pressure on the system, low speed, you can go from 277 CFM to 1376 CFM on tap 9. So When you're setting up air conditioning, you can either do the static pressure, look for the proper airflow, and change your speed tap accordingly. Okay, and that's an electronic speed tap, so it's done internally on the furnace. And again, it's done through the menu and the option button on the furnace, and we will cover this in more detail with the furnaces, but that can all be done through there. Or if it's a 9-tap furnace, there's ways to check it. But again, you have 1 through 9, and if you get past tap 5, it actually starts to combine taps to get the proper airflow. But backing up just a little bit, this is probably key. If you got a 3-ton system and you got a 0.5 static, you want to set that cooling tap on tap number 7, okay? If you have a 0.9 static, you've got to be up on tap number 8. So if you know your static, you can set up your airflow pretty easily on these furnaces. Now, if you don't want to do that, you can always do the old way of just, hit and miss. So when you talk about airflow, proper airflow, it all depends on humidity and how much is in the space. So if I have a home that's 80-degree return air dry bulb and 73-degree wet bulb, my temp drop on that coil is going to be 12 degrees. Okay, as the humidity comes out of the space, as the enthalpy changes, that temperature rise is going to increase. So at here, my sensible latent split is probably 40-60. Okay, as the humidity comes out of the space, my sensible latent split here is maybe 20-80, and I'm getting better airflow through the system. So just remember, temperature drop through the coil depends on the humidity in the space. So if you've got this chart, or if you need this chart, let me know. But it's a great chart, and it works on everything. I've used it for years and years and never let me down. There's also a sensible latent split, okay? So just remember, when you're selling an air conditioner, you're putting in an air conditioner, that if it's 85-degree outdoor and the wet bulb indoor is 71, in other words, it's pretty humid, at say 78 degrees, I'm getting 13,000 BTUs of sensible cooling out of that unit. I'm not getting the full 2 tons. I'm still getting 27,000 BTUs, but 13,000 is sensible. The rest is latent. It's all working on humidity. So that's all latent load. As the humidity comes down in the space, now my sensible cooling will be up about 22,000, and my latent drops to, well, that's actually total capacity, 22,000. So if you look at it, a 2-ton is not really a 2-ton. There's always that sensible latent split. You're never going to get 24,000 BTUs out of a 2-ton unit for sensible cooling. There's always that couple thousand BTUs that's latent load that you really can't count into the calculation. So if this house was really a 2-ton system, if it was 24,000 BTUs required, you'd be a little bit short on the hot days right here. So always, keep that in mind also. Reusing line sets, as long as you flush them and clean them, you can reuse line sets anytime you need to, provided they're properly sized, okay? Now, charging, I showed this slide earlier, but beer can cold and sweaty. Basically, the charging hasn't changed in 100 years. I mean, the compressors were a little bigger back then, but basically the refrigerant chart is the refrigerant chart. So if you put a set of gauges on a system and you see these numbers, what that's telling you is that 118 pounds of R410 is a 40-degree saturated coil, okay? 365 pounds of head pressure is 110-degree saturated coil. So that's telling you what your saturated condition is in the evaporator and in the condenser, okay? The gauges just give us that saturated condition. That's all they do for us. So if you want to see if you're properly charged, and I'm going to jump ahead here again, guys. On a TXV system, we charge by subcool. On a non-TXV system, we charge by superheat, okay? Typical superheat is 8 to 12. Typical super or subcool is 8 to 12. All right. We must be at 400 CFM per ton. In other words, make sure we've got good airflow through the system. And if you're not sure if it's a fixed orifice or a TXV, there's a really simple way to do it. Restrict the condenser fan. If the suction maintains while the high side rises, it's probably a TXV, because the TXV is going to try to maintain the same superheat no matter what the head pressure does. If the suction and the head pressure rise simultaneously together, it's probably a fixed orifice, and then you charge by superheat. Okay. If you can't, see the TXV or the metering device, that's a simple way to kind of see what's going on. Now, if it's a non-TXV, then we charge by superheat. So basically, if you have a condenser outdoor unit, I'll just pick 80 degrees here. And my return air wet bulb is 73. My superheat's going to be 27 degrees. And again, this is sensible latent load. So as that humidity drops out of the space, as that latent sensible split changes, now we're down to maybe 8 or 10 degrees or 6 degrees. If we're at 61 degree wet bulb and 80 degree outdoor, we're at 10 degrees. So what happens in this area here? You never ever go below 5 degrees of superheat, no matter what the conditions are, or you will take a chance of flooding the compressor. So non-TXV systems, make sure you use a superheat calculation to charge the unit properly. Okay. I'm going to skip by some of this, guys. So we want to get to just superheat. So on a system that has an expansion valve, we charge by subcool, but we monitor the superheat. So in other words, we charge to 10 degrees subcool. All that's telling us is that we've got high pressure vapor leaving the condenser or leaving the compressor. We're hitting the condenser and we're condensing that high pressure liquid back or vapor back into a liquid. We're sending liquid to the expansion valve. The expansion valve has to see liquid in order for it to work properly. And the expansion valve is metering out a saturated vapor liquid low pressure. And the evaporator is picking up heat, and that superheated gas is going back to the compressor. So on a expansion valve system, we like to charge to 10 degrees of subcool. So what that means is if I have a pressure of let me jump ahead one slide here, I believe. A couple of slides, bear with me. Okay, so for proper subcool, we want to make sure that if the system is, here's a good example. If I have 317 pounds of refrigerant, that equates to 90 degrees, okay? So that's the temperature pressure chart relationship. I'm sorry. That equates to 100 degrees. So the PT chart at 317 is 100 degrees. If I read the liquid line and I see 90 degrees, that's telling me I have 10 degrees of subcool. Okay. And 10 degrees of subcool, if you look at this, means that I've got a full column of liquid feeding the expansion valve, okay? If you put a sight glass in a system and you put the sight glass right here, all that tells you is you have liquid leaving the condenser. It really has no effect on whether you're charged properly or not. Okay, so if you're going to put a sight glass in, it needs to be in front of the expansion valve in order to let you know you do have liquid hitting that valve. But you still have no idea how much liquid, because if I have 10 degrees of subcool, which means I'm flashing from a gas to a liquid somewhere around here, and I'm sending liquid to the valve. If I've got 20 degrees of subcool, well, now I'm flashing into a liquid somewhere halfway in here. If I've got 30 degrees, I might have a flooded condenser. Okay, if I have a flooded condenser, that's going to mean this pressure is going to be higher. The compressor is going to be working harder. It's going to be costing our consumer, more energy at that point. So A sight glass is okay to tell whether or not there's liquid here, but it really is not a good way to charge a system. Okay, you know, do it by subcool. 10 degrees subcool means you got a properly charged system. If you don't have any subcool, if it's low, if you've got, you know, 2 or 3 degrees of subcool, well, then you're not feeding liquid to the valve. And if you're not feeding liquid to the valve doesn't know how to feed the system. So you're going to have high superheat. You're going to have high temperature gas here. It's not going to cool properly. System's just not going to work. This needs to see 8 to 12 degrees of superheat. And in order to do that, it has to see liquid at the valve right here. Okay. So 10 degrees subcool, we feed the valve liquid. The valve's happy. It feeds the evaporator properly. The expansion valve's job is to try to maintain somewhere between 8 to 12 degrees of superheat. Some of the more high efficiency systems, you might see 18 to 20 degrees of superheat, okay? So just make sure that we're feeding that valve properly, and that's what the subcool is telling us. As long as the valve's fed properly and we're 8 to 20 degrees of superheat, the valve's probably working fine. And it's feeding the compressor the way it needs to. Everything should work at that point. If this is at 0, if we don't have any superheat here, then we have a flooded coil. When we have a flooded coil, that usually means that we either have, you know, we've got dirty filters, we've got bad airflow, we got a broken belt, we've got, you know, some issue where we're not picking up any load. Okay, we're not doing any work at that point. Expansion valve system, you're probably not going to flood the compressor. Not a big deal. If this were a fixed orifice and we had 0 superheat here, we'd be sending liquid back to the compressor. Okay, so that would be a really not a good situation. Okay, so what happens if I have high superheat here? I'm say 28, 30, 40, 50 pounds of superheat. Could be almost anything causing that. High superheat here could be we're not feeding liquid to the valve. Okay, so first thing you want to do, of course, is check to make sure it's charged properly. If we are feeding liquid to the valve, we've got our 10 degrees of subcool, and we're still seeing high superheat here. Could be a couple of things. Could be a high load. I've seen cases where the ductwork came apart in the attic and we're drawing 140-degree attic air through there. That'll drive your superheat through the roof. We could have crap in the valve. We could have, I remember a couple of years ago, we actually had can't remember what the MJX oil additive we had to put in there. The valves were plugging up, and then what would happen is it wouldn't meter properly, and we'd see 40, 50 degrees of superheat. That's a bad valve. You know, before you replace the valve or before you condemn the valve, make sure you got a good charge. If the charge is right, and we're still getting 40, 50 degrees of superheat out of this, and the return air is normal, the blower is working, the filters are clean, everything checks out on that, and then you probably have a bad valve at that point, okay? So it's the basic refrigeration cycle, and all the valve is doing is it's reacting to this temperature right here, and it's opening and closing the valve to keep the proper amount of refrigerant in the coil. Again, could be 20 degrees of superheat, could be 22, 23 if it's got a really high return. A new system you just put in on a 90-degree day, it may be very high until it gets to the house. But you know, don't condemn the valve till we've looked at all the other things. So I guess that's I did a real quick session here on you know, charging. If you guys have any questions, you know, throw it on chat or unmute yourself and ask me. I'm going to just go through some of the rest of the presentation here and see if there's anything that I want to take a look at. And yeah, this is actually, as long as we're doing it, let's take a look at this. So if I have a system and I'm looking at the subcooling to make sure it's charged properly, I've got an R410 liquid line pressure of 340, liquid line temperature 105. I've got a PT chart that shows 105. The actual line temperature is 105. I have no subcooling at that point. My system is starved. It's undercharged. So the lower the subcool, the lower the charge. The higher the subcool, as in the next example, the higher the charge. No, previous example, sorry. Yeah, the higher the subcool, the higher the charge. So this is a flooded system. This is an overcharged system. If you see 30 degrees of subcool, and this is a undercharged system if you see 0 degrees of subcool. Now, there's some rules of thumb. So when you're looking at a system on an expansion valve, if I've got low superheat, I've got high subcooling, I probably have an overcharge, okay? If I've got high superheat, low subcooling, it's probably undercharged. We're not feeding refrigerant to that valve. High superheat and high subcool, we may have a restriction in the system. That's one thing that if you get into a system before you change an expansion valve, sometimes it's not a bad idea to take a temperature reading of the suction line at the outdoor unit and the indoor unit, and the liquid line, also outdoor unit, indoor unit. Make sure they're the same temperature. If your temperature outside is say 100 degrees on the line and it's 70 on the inside on the liquid line, you got a restriction. It's flashing off somewhere. Okay, so make sure you don't overlook restrictions. Make sure that when you look at the dryers are plugged at 3 degrees. So if you have a temperature drop of more than 3 degrees, that dryer should be replaced also. So things to look for when you're doing some troubleshooting on these systems that you can catch pretty quickly. The last thing I'm going to throw on here is microchannel, and I'm not going to spend any time on it other than to let you know there are microchannel units out there. We stopped making them a few years ago. And there's still some manufacturers that have them out there. And our rooftops, the Trane and American Standard rooftops are using microchannel. That's a different animal, okay? So microchannel, if they put it in terms we can understand. If spine fin is like a keg of beer, microchannel is like a can of beer. There's that much difference in the way they work. But when you look at microchannel, there's a charging chart, and it's like an approach temperature. So if you put your gauges on there and you see these numbers, okay, 97, 107 is where you should be, and your high side is 414. If your pressures are below this, you need to add refrigerant. If some of your pressures are above this, you need to remove refrigerant. So I'm not going to spend a lot of time on it, but there is a chart specific, and the 2-ton and the 3-ton are different. So just make sure if you run into microchannel that you don't charge it by subcool or superheat. It's a whole different animal. It's got to be done totally different. So, okay. I know I ran through that real quick, but I'm at my time limit here. So if anybody has any questions, you can put them in chat, or you can unmute yourself and we can talk. Otherwise, thank you for your time this morning. I appreciate it. And
yes, thank you very much.
Yeah, I hope you got some good stuff out of it. And if you need anything, give me a call. You guys all know how to get a hold of me. So
thank you for your time, sir.
all right, have a good day, people.